Historically, maintenance data meant keeping simple history logs. Today, it's a predictive decision asset. But there is a mechanical problem at the starting line. Different crews use localized naming habits. One technician types pump broke, another enters pressure drop, and a third types seal failure. This creates semantic chaos. Human supervisors can read those three entries and deduce they mean the exact same thing, but databases and machine learning models cannot. When closeout notes rely on free text, standard reliability analytics mathematically break down. You cannot calculate mean time between failures or run a Weibull analysis if the software registers three entirely different problems. Purchasing advanced predictive software cannot bypass this bottleneck. If the underlying data is fragmented, the model spends its processing power analyzing noise instead of finding patterns. Industry standards like ISO, EN, and IEC are frequently dismissed as bureaucratic compliance checklists. This diagram shows what those standards actually form: an interconnected standards stack. It operates as a required engineering schematic for processing industrial data. Every layer dictates precise, mechanistic rules for how information is captured, stored, and moved across a facility. Applying these layers ensures that isolated, messy maintenance records unify into high-velocity, interoperable decision assets. Mastering this architectural stack serves as the mandatory prerequisite before a facility can transition into an AI-ready digital environment. We start at the foundation: governance. The ISO 55000 series defines the core principles of asset management. It demands a shift in the organizational mental model. The physical pump is an asset, but its curated failure history dataset is a managed asset of equal value. ISO 55133 operationalizes this concept. It mandates systematic oversight for data throughout its entire lifecycle, establishing strict rules for creation, storage, and eventual disposal. This clarifies the difference between raw asset data, like a single temperature reading on a Tuesday, and curated data assets, which are validated, standalone failure histories ready for analysis. Without strict governance enforcing these rules at the base layer, data inevitably degrades over time, invalidating every operational decision made above it. Moving up the stack, this hierarchy demonstrates the structure required by ISO 1424. It eliminates free text variability, forcing technicians to select from structured libraries based on specific equipment class. The primary innovation is decoupling a single failure event into a triplet of distinct codes. First is the failure mode. This captures the observable effect on the function, like failing to start. Second is the failure mechanism. This isolates the physical process causing the issue, such as bearing seizure. Third is the failure pause. This identifies the underlying human or operational reason, like a missed lubrication plan. Compare a useless free text entry like pump broke against that exact same event structured into the rigid mode, mechanism, and cause triplet. Enforcing triplet coding at the software level acts as the only structural defense against the garbage in, garbage out cycle. Rigid data structures fail if the human workflows capturing that data remain inconsistent. EN 17007 provides a reference framework that standardizes the actual process map of maintenance. It dictates exact workflows for planning, execution, and support. This solves the measurement problem. Benchmarking across multiple facilities is impossible if each site defines metrics like downtime or availability using their own math. This formula illustrates EN 15341. It provides an unalterable library of key performance indicators, linking separate plants together under a single mathematical truth. Leadership must standardize the organizational dictionary before they can trust the operational numbers. Examining the horizontal movement of data across an enterprise reveals that the highest risk of information loss occurs at system handoffs. The largest gap exists between capital expenditure project construction and ongoing operations. This flowchart illustrates the CFIHOS standard. It acts as a structured handover specification, preventing engineering data from evaporating before it reaches the maintenance database. Alongside static project files, a real-time stream enters the database, carrying operational technology sensor data. The OPC UA standard ensures this real-time OT data carries essential metadata context. It attaches the source device, an exact timestamp, and signal quality to every raw number. Interoperability standards prevent multi-million-dollar asset data from dying in isolated functional silos. We reach the top of the stack, the digital frontier, containing AI predictive models and digital twins. A digital twin built according to ISO 23247 will completely fail if it is not fed by the structured taxonomy of ISO 14224. Highly automated systems also introduce severe vulnerabilities. If maintenance work orders trigger automatically from sensors, the data pipeline requires impregnable defenses. The IEC 62443 standard provides the critical operational technology cybersecurity controls required to protect these industrial systems. In a connected ecosystem, cybersecurity functions as literal reliability insurance. It prevents spoofed sensors from causing spoofed maintenance. Look at the framework now as a fully functioning, layered ecosystem. Information generates at the baseline and travels cleanly upward. This seamless flow bridges the gap between engineering and finance, using ISO 5510, guaranteeing that technical actions align exactly with financial ledgers. The operational result is a drastic reduction in the cost of curiosity. Organizations stop wasting thousands of hours finding, cleaning, and arguing over data. These standards do not exist as a menu of isolated options. They form an interdependent chain where each link is mandatory. Implementing the standard stack ensures that human intelligence is finally spent analyzing asset reliability rather than cleaning up semantic chaos.